in a program, if you don't have one, you can see that we're going to have a very enjoyable next hour and a half or so. We do have a break in the middle. I'll be giving speakers a 2-minute warning, waving my hands, and then come up physically to stand next to them and start violating it. I need it more than anyone else. So I told Miller to do that for me. I'm the first speaker after Miller's brief introduction. I'm delighted that you could all make it. The launching of this fantastic book, big, thick book. Lots of reading you can do over the next month. If you buy a copy, I'm sure that all three authors will be happy to make a description to anyone you want. If you want to give it to your great aunt or whatever. So let us get started. Miller's going to start off with just a general introduction about the project that led to the book.
Thank you, Woody. I'm going to start very briefly with recognizing 5 people. Because without those 5 people, we wouldn't be here today. There's Hastings and Liz sitting right here. Son and daughter-in-law, Joe Pawsey. And you can read in the book, the preface, the incredible contribution they made in the book. If I started that, I'd be here for the next half hour. But the next person is Robin Harrison, that some of you know, who was our book editor. She was a former colleague at NRAO. She was our book editor. And without her, I'm quoting Claire now, without her, the book would never have happened. She made it happen, and we owe her a lot. And without Robin, we wouldn't be here today. Then Ron Eakers, who's some of I've seen already. There he is in the middle, who's unable to be here. So the third author, former director of New Mexico operations in New Mexico, and before me and following Campbell Wade. Then I'm going to mention Campbell Wade, who's sitting here. One of the 2 people in this room that actually met Joe Pawsey, because Campbell was a postdoc with Joe Pawsey in 1957 and 1959 in Australia. And in the early 60s, Campbell played a key role, and you can read about this in the book, when Joe Pawsey was dying. And there's a great deal of sad memories there. But thank goodness that Campbell was able to help look after Joe as he was diagnosed with cancer and eventually died a few months later at age 54. So let's talk about my involvement. My involvement started in 1966. I was a graduate student at Berkeley with Harold Weaver. Some of you know him, famous investigator of the structure of the Milky Way. Visitors would come frequently to Berkeley, and we had 2 famous visitors that year, Frank Kerr and John Baldwin. John Baldwin was on his way to become the first chancellor lecturer later that year in Green Bay. Frank Kerr said to me, "Why don't you come to Australia?" He knew I was interested in galactic structure. I was working on others. He said, "Parkes Radio Telescope," which was only a couple of years old at this point, would be a great place for you. And I thought, gee, I think we'd like that. Based on that conversation, I'm here today. And Frank Kerr was so appropriate because Frank was hired during the war after he graduated from the University of Melbourne in 1940, the same year that Joe Pawsey had joined the lab coming from Britain to work on air defense radar. There's page after page in our book about the incredible success. And when you read that book, that part of the book, you'll realize something that I always say to colleagues here. We radio astronomers are descendants from radar. Radar engineering in World War II led to where we are today. We didn't know any astronomy. Joe Pawsey didn't know about precession, for instance, and he was so mystified by the fact that the sources were changing over time because of precession. He learned a lot, and he met a lot of astronomers. John Bolton It's another story. And there's a slight anecdote in it. If I run over time, I've got 2 minutes. I'm going to have to finish the story quickly. He wrote a letter after he was visiting Berkeley to the big boss in Sydney, Taffy Bowen. And he says in the letter, "Dear Taffy, I met Goss in Berkeley. I don't have any impressions. I don't know if he's any good or not. But we don't have to worry. He's going to bring his own money, so let's hire him anyway." So my career started because John Bolton didn't have an opinion on me and Frank did. And Frank is so important today because 2 people in the audience, I'm looking at both of them now, attended are descendants of Frank Kerr. Exactly. Our moderator and his last PhD student who's sitting right here, Trish Jennings, who is the AD for New Mexico operations. And it's so appropriate that we're honoring Frank Kerr, her thesis advisor. The last sentence I want to make, there's a lot of legacy here. And one is tempted to rephrase what Isaac Newton said to Robert Hooke in 1675. We can see so far because we're standing on the shoulders. Here's where I invent my own part of the statement. We're standing on the shoulders of the radar pioneers from World War II, including Joe Pawsey. So we are standing on the shoulders of Joe Pawsey here, and it's so fantastic that his family is here and we can commemorate his life.
So in 10 minutes, and Millie, you're going to give me 2 minutes warning. I need it more than anyone. I'm going to try to summarize this critical role in regular astronomy as a whole and set the context of the post-war era, which I studied greatly in a book called Cosmic Noise that came out in 2009. Here's the terrific trio in the preface to the book. It's a great photo. I don't know if were the dishes photoshopped on the back, or is that genuinely that you were posing there?
I think it's genuine.
No, it's the actual shot.
Everything in the book is real. So in 1960, the Australian Broadcasting Corporation, ABC, had a TV show called Horizons. And Joe Pawsey and another astronomer named Giovanelli. What was his first name? Ron Giovanelli. And it's marvelous because when Joe is first asked questions by the moderator, he goes through his early life. And so I'm going to play 3 minutes of this. And I hope that it will work from a technical point of view. Also to those online, we tested it out. I think I better go out. I'll do it this way.
Presently, they'll be talking to one another. But in the meanwhile, Dr. Pawsey, where were you born, sir?
I was born in Ararat, Victoria.
And where schooled?
Well, I went to school in country high schools in Camperdown, Victoria, and then I went to Melbourne. I got a scholarship, and that took me to Melbourne. I went to Wesley College in Melbourne.
Yes, and the university.
And went on scholarships to the university, and my life has been governed quite a lot by scholarships, because from Melbourne I went to Cambridge because I got an 1851 exhibition scholarship, so that I went to the Cavendish lab in the great days of Rutherford.
That must have been a wonderful school. I was talking to Sir Leslie Martin the other day, who was also in the Cavendish under.
Yes, he was a year or so before, some years before me.
Yeah.
But it was absolutely outstanding in the world in those days for its achievements.
Why?
Because Rutherford had such a remarkable flair for research.
A flair for research.
Well, he could devise simple experiments that led to the right to answers that really meant something. And these 1931-34 days were the days when the answers were coming quickest. The groundwork had been built up, but this was the most spectacular period, I think, of the whole lot.
Was it all very expensive and on a very large scale?
Oh, no, the Cavendish had a tradition of brains and sealing wax and string as the description of the equipment. Well, it can't be carried out these days, but you'll find that Cavendish people all over the world have a great longing to be able to do experiments in a simple fashion. There's a tremendous advantage if it can be done.
Is this analogous to the mathematicians talking about elegant proofs?
Well, I think so, exactly.
Yeah. And radio astronomy. Well, let's begin with astronomy. Why did you become and how did you become interested in this?
Well, I became, I had done very little astronomy or no astronomy until the end of the war.
Yes.
Then I had a background in physics research and in the technology of radio, because I'd been working some years in England on the early development of television and then on radar in Australia.
Yeah.
And we were interested in finding really interesting things for research. Now, there was a complete mystery evident to us in those days. A man from America in the early 1930s had discovered radio waves coming from the Milky Way. And this seemed to be worth trying to find out something about. Then the thing was complicated by the parallel discovery of radio waves from the sun.
Yes.
Our first work was using equipment which we got from radar aerials and receivers and so forth, and we were able to observe the radio waves from the sun.
But the fact is, you were fundamentally a physicist.
Oh, yes. And I knew very little astronomy.
Dr. Gervinelli, you're a physicist. Can you explain?
So in the post-war years, this was the sky as viewed by what I call Homo radio. You had the Milky Way, it corresponded with the visible Milky Way, but it was much broader in its extent. You had more brightness towards the center, which didn't exactly correspond to the Milky Way somewhat. You had some individual sources, Cas A, Cygnus A, Virgo A was out of the, just as strong virtually, and yet it was way away from the plane of the Milky Way. And then the sun, well, the sun was not as bright as some of these at 100 megahertz, at these low frequencies that were commonly used. And that was a real puzzle. And then you had these scattered things all over the place. What were they? They were called radio stars in the beginning. So this is a completely different view of the universe than you had in traditional astronomy. This is showing the technical details. There's the low frequencies down here, the high frequencies, the moon, the quiet sun, but you could have a disturbed sun that was 10 to the fourth, 10,000 times brighter. And you can see even here, the quiet sun is much brighter at these frequencies than some of these very strong sources. So what is going on? Receiver sensitivity was much better down here, and so people focused on this area. And it wasn't until really 10 years after the war that you began to have receivers that could do some good work in the centimeter waves. In cosmic noise, I identified various themes. Pawsey played critical roles. Let's get that pointer out of the way here. Where is the pointer? Can someone get it out?
Okay, let's do this one.
Yeah, I don't want a pointer. Get that red one, please. Early radio astronomy, as Miller was saying, was shaped by World War II and by the Cold War, as you get in the post-war decade. Radio astronomy was techno-science. One of the questions I was interested in, I could never get an answer satisfactory to myself was did science lead the technology or the technology lead science? No, it's a back and forth. It's a dance. Neither person is leading. Overall, this opening of the entire electromagnetic spectrum was what I call a new astronomy. This term has been used all the way back to Kepler. No less important than the new astronomies with Galileo, Kepler, Herschel, and 19th century astrophysicists when photography came in. It was all triggered by new technologies. Radio astronomy was right along in that. And the other thing is that this new astronomy isn't just radio astronomy. It was all the other parts of the electromagnetic spectrum that were opened up in the X-rays, gamma rays, UV, infrared. They all followed on, and they were much more easily incorporated into astronomy. And there was no arguments about whether you were an astronomer or not, because we've seen this before. The radio astronomers are pioneering it from a sociological point of view. Pawsey himself wrote that his great strength was not being brilliant, this is to his mother, but through picking the right things to do. He called it following his nose. Well, that doesn't really explain it. I mean, we all follow our nose. The question is, you need to smell things properly and go towards the smell. He was the arch empiricist. There's so many examples of this. He used to say, suck it and see. That's the way you find out about the world, not sitting there and thinking, well, we'll do this, we'll do that. No, suck it and see. When he visited the labs that were scattered all over the Sydney area, you would always want to twiddle knobs, which would upset the people that were doing the experiments because they understood what was happening, but he just wanted to see what would happen. And so it's even said that a couple of them put in fake knobs, twiddle, they wouldn't do anything. The key people in radio astronomy in the post-war decade, even 2 decades, Mills, Bolton, Christensen, Bracewell, Kerrigan, Wild, and many more, they overwhelmingly supported Pawsey's own analysis of his skills. And what were those skills? He learned from his years in the 1930s at the Cavendish, as we heard him say, and secondly, from the wartime development of radar technology, from leading teams under constant pressure. How do you motivate them? How do you get the results that you want? He had a quiet manner, an honesty, a confidence that was just very rare, even in any walk of life. A lack of guile that were key traits that instilled loyalty in his team members. Some call him almost childlike in his curiosity, in his trust of people, and his delight in new discoveries. By the way, those years, in 1932, plus or minus 1 year, you had the discovery of the neutron, the positron, antimatter. You had the first cyclotron developed at Berkeley. You had the first transmutation of one element into another. All of this happened in that 2 year period. He was right in the middle of it. But that was not his thesis. His thesis was to do with the ionosphere, the electrified layer high in the atmosphere. And that will play a role in his first experiments on the sun after the war. I'm not sure if you guys mentioned it in your book, but in the West, the term radio astronomy was first used by Pawsey in a letter. That's the earliest I've found it. It was introduced in the USSR, but there was very little connection, published in Russian. There was very little connection between the West and the USSR in those days. Together with Ron Bracewell, that many of you heard about, and I hope that those of you that weren't, did not attend my earlier talk can come out to the, okay, we got to, Pawsey and Bracewell, radio astronomy, 1959. It was the Bible. That was a very important thing he did. He always wanted to forge vital connections between different fields. The real astronomers, the engineers, physicists, the ionosphere experts. And together with Tathy Bowen, the two of them had complementary personalities. They wanted to both make international connections to observe and learn from research activities and styles, to foster conferences, personnel exchange. Well, we heard about personnel exchange. Miller is not quite in the post-war decade era. He was born, but he's talking more about the 60s. And seek novel funding as he got into the 50s and the projects became big. And Pawsey's signature is out there. You can see it tomorrow. And here he is. Unfortunately, his picture does not show the actual pier that he was doing it. But here's Govan Scorp, an Indian radio astronomer, and Ron Bracewell on the left. Field stations were scattered all over the Sydney area. And we're going to talk very briefly about the two that he first worked on with the sun. And this is a marvelous photograph. He would go out and visit these and try to every 10 days get to all of these stations. And then they would have a big meeting every 2 or 3 weeks where they'd all be together. Here he is with Ruby Payne Scott, the first woman radio astronomer, and Miller's written a biography of her called Under the Radar. And here he is visiting at Pot Sale in the Sydney suburbs. Here's the kind of radar they were using in the beginning. I won't go into details given the time constraints. And this was something that came to be known as a C-clip interferometer, where if you look on a cliff at a source that is just rising above the water, you will see the direct wave from the source and you will see a reflection. And so with one thing, you can have these two interfering signals that will give you detailed knowledge. In this case, the sun was rising, and then boom, all of a sudden you got these bursts. What was going on there? And then eventually the signal passed out of their beam. And they determined that there was a sunspot, a huge sunspot, one of the biggest of the last century. They were just very lucky in that regard. And that it was coming from the part of the sun that their antenna signals had indicated.
Time's up.
Okay. And Miller's already alluded to it. But, I turn out to be a grandson in the academic sense of Pawsey, because Kerr was definitely a mentee of Pawsey, although he did get a PhD under him. And I was one of Kerr's first students, and Trish Henning was his very last student, I think, 20 years later at the University of Maryland. And these guys, Jim Heidman and Paul Wild and Chris Christensen, are all Australians. And here we have an American and a Dutch guy that were in the 21 centimeter business at that time, the Hydrogen line. Thank you very much. Oh, I'm now the moderator. And the next talk is from Hastings Pawsey, Joe's son, on Joe Pawsey's early life.
Well, good afternoon, everybody. It's very exciting and a great pleasure for me to be here and to also see so many interested people in a book about a bloke called Joe Pawsey. I'd also like to welcome those watching from overseas. I know there are a few Australians up there, so to the Australians watching, family and friends, g'day. I'm here because a book has been written, and this is the formal launch in America of Joe Pawsey and radio astronomy. It's an amazing book. It's about an amazing bloke, and he had a skill set which endeared him to an amazing career. He had scientific background, obviously. He was a researcher. He was a good organizer. He was a good administrator, and he was a good person at a personal level. So all of that is written about and beautifully explained in Miller and the two co-authors' book. However, to me, he was just Dad, because I was only 17 when Dad died. Dad was 54-year-old and obviously not yet at the peak of his career. So I knew him as Dad. He was a good friend of mine. He helped me educate myself. He was a good teacher to me, but he was just Dad. I knew he was a radio astronomer, and I thought I knew a little bit about it. And I also knew he was a physicist, and I had trouble spelling that word. Anyway, Joe Pawsey, you've heard him tell you a little bit about his background. I'd like to just emphasize a little bit more of that. The Pawsey family migrated from England in 1850, looking for better opportunities to the problems in Suffolk, where they came from. They arrived in 1850. There was a son and a grandson, and Dad was born in 1908 of two parents who were farmers on what I would call a subsistence farm, poor. However, his two parents were incredibly interested in education in the broad sense, in social consciousness in a broad sense. And as a small example, my grandmother probably left school, we're not sure, maybe at 11. Most girls didn't do much schooling on a small farm area then. But at 21, and this is around the turn of the century, she decided to go back to school to become better educated. It was only for a year, but that stood out at the time as very unusual. So two parents, very interested in education, one son only, but no money. And so Dad was homeschooled, home educated in the rawest form, not like we talk about today, until he was 9 years old. Then he went to a couple of one-teacher schools for a year or year and a half, but then life changed. He got a scholarship, his first scholarship, to start high school in a town about 12 kilometres away, to which he used to ride to every day on a horse. So he had 2 years at Camperdown High School. Then he was lucky enough to get another scholarship to go to a big school in Melbourne, Wesley College, a big comprehensive school, well up in the best schools of Melbourne. The scholarship paid, obviously his parents didn't. While he was there, he did well, but something extraordinary happened. He was offered a trip to go to Europe. Now, the organisation that took him was called the Young Australia League, an Australian organisation, and they would take boys, obviously only, and let them see other parts of the world to educate their understanding of a broader world. So away he goes with about 250 boys, tours all through Europe, meets kings, mayors, premiers, dined and wined, received keys for cities, and also saw the destruction, which was remnant still of the First World War. And I think that trip gave him two inspirations. One was he loved the concept of internationality. He liked the concept of more than a farm in the Western districts of Victoria. But secondly, I think it gave him an understanding of what war is about, and probably translates to his lack of desire of war and secrecy. And that's an important element to remember. So from school, he then got a scholarship, would you believe, to go to Melbourne University to his Bachelor of Science. And I have all his results from his schools, his universities, and he did well, to be very blunt. He then got another scholarship to do his Masters of Science in Melbourne. And then from that point, he got another scholarship, as it was mentioned by himself, that was the 1851 Exhibition Scholarship, which was being issued to people in the Dominions, colonies, to be better educated in the home country, England. You couldn't do a PhD in Australia then, so he went to England where he did his PhD. Now you will hear a lot more about him after that, which I will leave to others who can explain in far better detail than me. But what I'd like to do is show you a few pictures of the man as he grew up. So if I can ask Teo to let me see if I can do this now. Okay, let's start off as a youngster. Yep, studio photo, and he's 3 years old, so it's about 1911. Pretty impressive, obviously. Now, he was a farm boy, and this is him riding on Jack Pawsey, one of the local horses that they had, and they'd go to the local village with a cart. There was no other way in the early days. So he's getting bigger and he's growing up. And now he's gone to Wesley College in Melbourne for his high school, the latter high school years. The important aspect of that photo is not him, but it's his uniform. His uniform was made by his mother. Now, she wasn't a seamstress of any sort whatsoever, and I'm presuming it was only a treadle sewing machine, but it doesn't quite look like it fits properly, but I'm sure he and his mother were very proud, and I'm pleased to see that. So here he is at school. Now he goes to Queen's College, Melbourne University. He was there for 5 years, doing very well, and that's what he looked like at 19. And then a little bit later, one of my favourites, he's in Cambridge. You've heard Miller, anyway, talking about his time with the excitement of 1931 to 3. Atom was split. He's looking at atmospherics, the ionosphere, how can make radio communication better, the form of his life. But have a look. He's going to university. How many of you here wore a mortarboard and cape going to uni? Don't see many hands. There may be someone there. But behind that, if you can look behind, this was the major transportation, a horse and cart. And that represents the period in which he really tuned himself as a scientist. Now, this is after he's 39 years old, and that's 1947. So he's still much the same. He always wore glasses to me, and so he's getting more mature. And he did receive an FRS from England, and he received that in 1954. He was 47 years old. And let's jump now right to the end. He's about 50 years old. It's a few years before he died, but that's my memory of him. A relaxed sort of person. He wasn't terribly formal in many ways. And so it's absolutely, to me, that's Dad. He might be a scientist, but that's Dad. So that's fun for me. And a little bit later on, the year before he, or the year he died, this is him. He hadn't been formally diagnosed with a brain tumor then, but he lost use of left arm and left leg, wasn't operating too well, and he died in November 1962. He's with a brother-in-law, and he looked after him very well as Campbell Wade looked after him amazingly well while he was sick in America. Now, I should have mentioned, there's two people in this room that have met my dad. I'm one, and Campbell Wade, the second, is over here. It's a great delight. I've met Campbell before, but what an exciting time. So some years ago, I discovered through Miller that the site of the first radio astronomy searching for radio waves from the sun took place in the suburb almost of where I lived, very close. So I made a campaign to get a monument built in Sydney to recognise the foundation, the birthplace of Australia's radio astronomy. On the 3rd of October, 1945, Dad went up to an existing radar station, which he knew well because he had 5 years of radar development, and they pointed the aerial to the sun, they switched off the transmitter and let the receiver do the work, and signals, strong signals. Only at sunrise, because the aerial rotated on a vertical axis, they couldn't follow the sun up, and then they turned it around, waited until the sun set in the west, and the same things. So that day is the beginning of Australia's radio astronomy and the birth. After 5 years of work with the local council, and you all know what it's like to work with bureaucracies, we had this structure built. You can see a panel in the middle there, and that panel basically says the birthplace of Australian radio astronomy. What more do you want to say? Yes, there's a few words there, and at the bottom right you'll see a QR code which you can look at and see a lot more information about the story. And part of the roof structure is a skeleton, a part of a sector of the sun. Obviously, we don't know too much about what's in the centre, but we can see what's on the edge of the flares going up. So that exists. I obviously have more intentions to make that one a little better. It was developed before COVID. We didn't have an opening before because of COVID. However, I remain optimistic we might get some more things. And Woody, one of the things I'd like to have is a sundial. I think I've met the right person. I met Woody first in 1978. He came to my house, looked through some of the archives that Miller mentioned, and that's the start of our relationship. So I just want to say a huge thank you to Miller, to Ron, g'day Ron, and Claire for helping him and many others that have helped produce a book over 20 odd years. I knew Dad as a 17-year-old. By working with Miller, going through my archive, listening to all the stories, I know Dad now as a man. And it's only through these people that it's brought him to life to me. And that to me is absolutely fantastic. So Miller, thank you. Thank you, Claire. Thank you, Ron, and everyone else. And it's just a delight to be here to listen more about my dad. Thank you.
Very nice, very, very moving even. Well, our next speaker is not an astronomer. She's a historian of astronomy, a sociologist of science, and I should say a historian of science. And she, Miller can tell us this evening how he connected with Claire, etc. Or maybe you're going to tell the story. But anyway, be a very different perspective. And she's one of the authors that has brought this book into a wholly different place than it would have been if it had only been by the other two co-authors. And her topic is Serendipity, the accidental rediscovery of Robert Merton in the history of radio astronomy. Claire Hooker.
Thank you so much, Woody. And there's a sort of subtitle there. And for those of you who don't know and are interested, it's Anne Green's fault that I know. I knew that there would be some here who would like to know that. I'm just beginning by acknowledging that we're meeting here in an area where people have shared knowledge about the stars and their significance and our place in the universe for tens of thousands of years. And I acknowledge the Navajo and the Apache and the Puebla peoples and the other first peoples who have been here before us, and the people of the Gundungurra and the Darug people whose land I am an uninvited guest on in my home. That's a photograph of near my house in the Blue Mountains, scene of many astronomical investigations. So what I wanted to do was talk a little bit about what I would think of as the methodology for this book. And this book does have a methodology, and it's super messy. Historians are quite comfortable and like messy methodologies. I think our book should be, the methodology should be described as conversational inquiry, because the things that I think make the book really interesting are the things that came out of the integrity of doing those conversations really well. So the book is the outcome of a collaborative process in which 4 people kept asking each other an awful lot of questions, often from positions of, considerable ignorance about each other. And we took the time to sort out the answers through those conversations. And I just would like to, at this point, say that being able to do that and to have the time to do that is an extraordinary privilege. And I want to really honour the value and the impact of that process. It's so eroded by the need to be very goal focused these days. And I know that very few people are afforded that kind of time, but it produces extraordinary insights. I hope some of them bring interest to different readers of this book. So the 3 authors had really different ways of thinking and really different views about what historical knowledge actually is. And the book is above all a tribute to Miller, who I have termed an antiquarian or public historian. I would be interested in Andrew's comments on this later on. Such historians are finders and custodians of the most complete and detailed record of the past that it is possible to create. And often their focus is on ensuring the integrity of all of those details and making sure that they're present. Ron, however, took the approach of what I would call a practitioner historian. So somebody who comes from an area of practice science, in this case, whose framework comes from looking for the things that are important to a practitioner, like how did discoveries come to be made, or who should we, what kind of significant ideas and techniques emerged and what made them possible. And from my perspective, from a kind of academic historian perspective, my focus was a little bit more conceptually driven. I used to say theoretically driven, and then radio astronomers told me that theory was math. So we are looking conceptually about historical circumstances and aiming to understand things like what kind of social systems or structures or processes might drive change or preserve continuities over time. And these ideas were refined by Robin, our first-rate godsend of an editor, who also is a key part of the intellectual integrity of the process, because through that process of refining ideas is how we got to where we are now. So the 3 authors, let me see, how's my notes are here, okay. So I think this is going to work in terms of my notes. For me, one interest is thinking about how doing science and doing history are similar or different. And I have what I hope is this image. Yes. Miller, this is Ken Bean's telescope here. Yes. And I've used this because I think it illustrates a similarity of exploring how much you can understand when you only have a tiny partial perspective. And if you can imagine opening the tiny slit on that roof and rotating it around, that's the kind of partiality that historians have also, because you can only have what you are able to see with the documents that have been left to you and the few skerricks of information, they're like data points that you can then put together. The questions we asked each other had to do with Joe Pawsey. Some you've heard about, how did someone from a very impoverished regional Victorian background become an internationally known physicist? We asked questions about how early radio astronomy in Australia came to be so internationally successful, which included asking questions about the impact of different leaders and leadership styles of the different very small number of different research groups at the time. And we asked questions about the science. Where would Joe Pawsey, Ruby Payne Scott and Lindsay McCready have even learned about Fourier transforms? How widely were those known at the time? Where did those ideas appear? What made it possible to think about them in a particular way? Why didn't Joe Pawsey see more potential in the first computers? And these sorts of questions, the questions about Joe the person, the questions about leadership styles, the questions about what made it possible to even think about a scientific question in a specific way, came together as questions about how to understand science itself. How does science work? And can understanding it allow anyone to do it any better? And in the process of asking that bigger question, we sort of tried on for size most of the major theories and concepts about how science works to see how well they described what we were seeing in these archives. And in doing that, we were of course following in Woody's footsteps, although I must say we retrod this ground conversationally quite independently, and then would say at the end of such a conversation, oh wait, what did Woody say in the introduction? Does he agree with us? That's how we kind of moved along. That's us having more of our conversational methodology. Sorry, it's a bit slow for me to make this slide move on. One of the things we talked a lot about was how to understand processes of discovery. Radio astronomers love discovering things, but to historians, the term discovery has a very bad name in history. And I can explain why by saying Christopher Columbus discovered America, Captain Cook discovered Australia. So calling something a discovery makes that act sound like a simple, truthful statement, as if you have simply picked up a bone lying in the sand. But actually what using that word did was, in the case of Christopher Columbus, make certain people's existence and experiences actually invisible and devalue their forms of knowledge. So in my historical language, I think of discoveries as constructions, as things you build out of the intellectual tools and the artifacts of the world as you come across them. I think of them as ways of seeing the past that allow us to see the world in particular ways. So I kept asking Ron and Miller, what would it matter if we thought about discovery in science as something that was done not by a person, but collectively by large groups of people? Or if we thought about it not as a point in time, but as a process or as a kind of unfolding? But of course, one never goes down these paths, or at least I find in my whole entire academic life, I never pursue a path of that kind where I'm asking a theoretical question without having to eat my words. And I had to eat my own words because I also experienced discovery as part of this book. And what I discovered, to my complete surprise, was Robert Merton. Now, Robert Merton, I knew about. He was the first scholar to understand, to try and formulate an understanding of science systematically by using what was then the relatively new discipline of sociology rather than philosophy. I'm going to be a little over time. I think I'll hurry up, and I won't tell you all about the way in which Merton thought, but he was looking for social structures to explain this, and he invented a whole bunch of concepts, including such things as unintended consequences and the self-fulfilling prophecy. And we don't know that he invented those things because of a phenomenon that he himself described, which is called obliteration by incorporation. It's so much part of the literature that you don't even notice that it's occurring. Merton had written this very key paper in 1942 that set out the framework for what became sort of regarded as a Mertonian paradigm to describe how science works. And it was this, that science only works because its social structure and system functions really well, and that social structure is oriented around what he thought of as 5 norms. And norms are both proscriptive, they tell you what you ought to do, and descriptive, they just say what are. These are the so-called ethos of science, and they were communalism, that knowledge belongs to everyone and should be shared. Universalism, it shouldn't matter what the characteristics are of the scientist who creates knowledge, it's true anyway. Disinterested, scientists pursue research for its own sake and not for personal reward. And organized skepticism, that all claims must be scrutinized at all times. We can discuss Merton if we like, but I'll just say that he saw that this ethos stood in sharp contrast to the partisan and prejudiced beliefs that had led nations to follow authoritarian leaders into war in 1942 when he published this paper. So Merton's model, actually, although Merton became no longer very popular by the 1980s as a way of understanding science, Merton's model helped us understand priority disputes that occurred in the work that we were looking at. That's one episode you can look at. They helped us understand why certain disagreements, such as about how to introduce, how to interpret the results of early surveys, were unduly prolonged. They helped us understand, as Ron will discuss, serendipity patterns, how much of these early discoveries came about because of an actually describable phenomenon of accidental discoveries that Merton was particularly interested in. Now, the usefulness of Merton's paradigm, that is, by the way, all of the authors. You'd like that, would you? And in fact, if I do that, I think I have a detail that will show that. So the usefulness of Merton's paradigm was a real surprise to me, because Merton's work had been much criticised since it was published in the 1950s and 60s. And to be honest, it had been largely dismissed in the field of science and technology studies from the 1980s, and I had barely learned about it in more than kind of superficial detail. But we were not the only scholars to find Merton useful for understanding early radio astronomy. The previous collaboration between Cambridge radio astronomer David Edge and sociologist Michael Mulcahy had similarly found it useful. So I was asking myself, why was this quite outdated model, why was it the one that kept becoming the thing that would explain things usefully to us? And then I finally realized that rather than seeing Merton's paradigm as a theory about science in the abstract, that I could understand it as historically located. It was written at a particular time in 1942 and developed in the 1950s and 60s. Coincidentally, that's the sort of science and exactly the time when Joe Pawsey was a scientist. So then I understood that Pawsey is the ultimate, the penultimate, the most classic Mertonian scientist. They were almost exactly of an age, born within 2 years of each other, lived through very similar periods of very similar outlook. Pawsey's integrity and ethos is defined more or less by the Mertonian norms. So lots of people said that Merton's theory wasn't very good because scientists, in fact, do not usually behave in a disinterested, skeptical, communal kind of way. But, you know, Pawsey really, really did. He was perhaps the greatest exemplar of that way of looking things, and his leadership was defined by these values, and in many ways, much of the work that would go less celebrated in a standard history of science, such as the huge amount of effort he put in to identify and standardize galactic coordinates, which let so much of the rest of the field function. It's not a discovery, it's not the sort of thing you get awarded a prize for. It's a totally fundamentally crucial communal infrastructure I see as the expression of this Newtonian norms. And he fostered and shared these values as core not only to doing science, but understanding them as core to the functioning of research teams and research networks, which we know he was so unbelievably and particularly skilled at. And incidentally, he independently created a fairly similar classifications of types of discoveries as Merton himself. And we have a little table that explains that in the book, and Ron may allude to it too in his talk. So thank you very much, and I leave you with that great discovery that theories of science are historically located, and science itself might change, and that we can understand that scientific ethos as something that was an animating principle behind the internationalism and the communalism and the excitement of a field as it grew into being, in part because of Pawsey's such significant contributions.
Fascinating, fascinating indeed. You didn't know he was a Mertonian. So now we move on to the third author with his particular view of the Pawsey story and the things that it elaborates. And that, of course, is Ron Eakers, the former director of the BLA. And too bad he can't be here in person. I was very disappointed, Ron, that you couldn't make it, but I'm delighted that Zoom allows it. He's going to talk about the evolution of radio wavelength interferometers in astronomy.
Can you unshare the current screen so I can share, please?
Somebody unshare?
Yeah.
Oh, here.
Well, I'm. I think we can share your screen now.
Okay, I forced my way in. So can people see that and hear me?
It's not on the main screen.
Oh, you see it, so that it.
So while we're getting that on the main screen, just tell me when you have it working, or I might be able to see it. I might just say, I'm of course sorry I'm not there with you, but at least I can participate online, and there's quite a group of us doing that. And that, of course, has depended on the technology, which was developed largely by radio astronomers. And John O'Sullivan, who was the inventor of Wi-Fi, which is essential for what we're doing now, came out of the groups which were started by Joe Pawsey. So have we got me on the screen yet?
Yes.
You're on the screen.
Yes.
Yes.
Oops.
Okay. Now, as Claire has pointed out, one of the great things that happened in this book was the interactions between the three of us. I knew quite a bit of radio astronomy before I got into this. I might have even thought I knew the history. But what I didn't know was the methodology that somebody like Claire brought to this story of understanding the connections between the progress and all the other things that were happening. So science doesn't occur in isolation. It occurs because of all of the connections and the circumstances. And by looking at this period in detail, I think we were able to develop a very interesting understanding. And I learned enormously from Claire. So it reminded me of a TV series in the period when I was becoming heavily involved in science in the 1990s. James Burke, it was a BBC program called The Connections. And he took various discoveries in modern science and explored where they came from. It was called The Connections. And so following that methodology, I thought, where did this interferometer first came from, which was key to our understanding of the universe using radio waves? And I'm going to give you a version of this story, which is not the most popular version, but this is what I understood. And in fact, my talk, the first half and the second half, are what I learned by writing and by being involved in the writing of this book that I didn't know before. So going back to 1910, Marconi has transmitted this incredible success of transmitting by radio across the Atlantic Ocean in 1901. Now, it's pretty interesting already that he was not a professional scientist. He was a very wealthy amateur. And the professionals, such as Oliver Lodge, had said this radio propagation, well, it can't go around corners, so it will have a very limited communication possibility. But Marconi ignored that, and he could, because he was an individually funded amateur. And so he went ahead, just driven by the potential to do something different, and succeeded in transmitting across the Atlantic. So what happened? Well, this is very interesting, and this is where Claire came into my life, making me read about the ionospheric physics and the way this field progressed in the late 1800s, early 1900s. And what was incredible and gave me a great insight into the way science works is how wrong the physicists got everything. The models of the propagation of radio waves were all about diffraction around objects. And when this disagreed with the observations were ignored. It is amazing to read how many eminent scientists were making incorrect interpretations. And then there's Oliver Heaviside, a practical man. He's the guy who invented coaxial cables, said if there was a reflecting layer up there, the signals would bounce around like they do down a coaxial cable. So he came up with the Heaviside layer, which Edward Appleton then was able to prove existed by a swept frequency interferometer system. And when you sweep when you have more than one frequency, you can separate delay and phase. So he was able to prove that there was a reflecting layer, which was in fact what Heaviside had predicted exactly, but which almost all physicists said, oh, Occam's razor says you can't make up things and put them there just because you want to explain something. But Heaviside was right. Appleton, of course, was a famous Cavendish physicist. So he got the layer named after himself and got the Nobel Prize. Interesting. Here's the diagram from his Nobel Prize talk. He's taking advantage of a very strong transmitter, which is the BBC radio, and he's getting a direct observation, and he's seeing the reflection of the ionosphere. Well, this is when Joe Pawsey comes into the picture, and here I owe so much to Miller, who has dug out all of these details, and Hastings as well, all the letters between Joe and his mother describing what happened when he went to Cambridge to do his PhD. So the Appleton layer had been discussed, and that was the context for Joe's PhD program. He worked with Radcliffe, and it was very clear that Radcliffe was the person who was providing the physical interpretation behind all of these studies. Absolutely critical role. Anyway, so for Pawsey's PhD, he was using this interference between the direct transmission and the reflected transmission to study the structure and the motion in the ionosphere. And by the way, the little sketch here is in Pawsey's handwriting, and it is in one of the many letters from Pawsey to his mother, as he describes in considerable technical detail the work going on in his PhD. Wonderful insight into how he was doing this. So now, end of the war, the emission from the sun had been discovered independently by a number of different people. And the question was, where was that radio emission coming from? How could we measure the structure of the radio sun. So here's Joe Pawsey's diagram. If you tip it upside down, it looks enormously like the Cliff interferometer that Woody has introduced, and I will just briefly say some words about. So the idea of the Cliff interferometer is identical, and Miller was perhaps one of the first to realize that, is exactly identical to what Pawsey was doing for his PhD. It's a great system for building an interferometer because you only have one receiver. You don't have to have phase stability between the different elements of your interferometer. And so it's a very straightforward procedure. And using that procedure, they got these interference fringes. Woody's already shown this diagram. This is the 7th of February, 1946, incredibly bright emission from the sun. I believe this is the first interferometer in radio astronomy. And you can see the connections now. It comes directly out of the ionospheric research. The literature, and I think including Woody, says it comes from World War II. World War II came from the same ionospheric observations. The use of radar in World War II to measure altitudes was being done by the same people that had studied the ionosphere. So it goes back to the ionosphere, to the heaviside layer, and back to Marconi doing an experiment that the theorists said would not work. Joe Pawsey, who was the first author of this paper when it was submitted, but the Royal Society alphabetized the authorship. In this paper, they describe using the C interferometer to co-locate the radio emission with the sunspots. So there's Joe Pawsey at the time. There is a later version of the Cliff interferometer at Dover Heights. And the other key person in this group, and the reason why Claire got involved is through Ruby, but you can discuss that story separately at some other time. Ruby, by the way, was the mathematician in the group. McCready was the engineer who built the equipment. It was Ruby who did the mathematical analysis, and that's all in Miller's book. Now, in that paper is this incredible statement. This is 1947. This is a decade before these discussions were occurring at the Cavendish. It is possible in principle to determine the actual distribution by Fourier synthesis using the phase and amplitude at a range of height and wavelengths. That is, in fact, the principle of aperture synthesis. And my assertion in looking at the history pretty carefully is this is the first statement in radio astronomy of the principle of aperture synthesis. Then one of the many groups which Pawsey had set up was Chris Christensen's group. And here is the interferometer he built, and by 1955 was using Earth rotation synthesis to make an image of the sun. Govind Swarup, who has also appeared in an earlier discussion, was a student, had come from India, and was working with Chris. And Chris gave him the job of taking all those Fourier components and making an image of the sun. And the way Govind had to do it was by hand with an electronic calculator. And Govind had estimated that it took him about a month to do basically a 16-point two-dimensional Fourier transform to get the image of the sun. Now, this is where the story goes off in a different direction. Despite the fact that they had made the first Fourier synthesis image, it was 20 years before the Australians ever computed with an electronic computer a 2D image. This was the 20 years where Cambridge, led by Martin Ryle, simply moved ahead and did many incredible discoveries using aperture synthesis. Was it because Cambridge had a computer and Australia didn't? No, Australia had built a thing called CIRAC. A guy called Pawsey had done that. It was almost identical in capability to the EDSAC computer at the Cavendish. And it happened to be in the same building as the radio astronomers, yet they did not recognize the opportunity to use it to do Fourier transforms. Here's Ron Bracewell, a quote he gave me quite some time ago, but luckily I wrote it down. I said, Ron Bracewell, how come you've got this electronic computer in the same building? Why didn't you use it? And Ron's response was, it never occurred to us that in the arcane art of machine language program and punching holes in paper tape would have any relevance to a radio telescope. They did not see the connection. And Mills indirectly made it even worse. As you can see in his quote, he just thought to include an electronic computer in the observing process was just not the way to do it. They're too unreliable, and the same Mills points. So Mills then had gone on to invent something called the Mills cross. And this is the way in which you can make an image through beamforming, which does not require any Fourier transform computations. So it is pretty clear that in Australia, the discovery of the invention of the Mills cross actually killed the development of the use of computers for aperture synthesis. And the path in Cambridge is then very different. Why did it happen in Cambridge? Not because those radio astronomers were any smarter, but because they were cheek and jowl with X-ray crystallographers who understood and were already using the electronic computer to do Fourier transforms. So you can see the connections now and the way in which these steps are made. So that led me to the story which Claire has introduced. This is how I discovered Robert Merton. And his incredible book on the travels and adventures of serendipity, in which he writes a book not to just give an explanation of any scientific principle or any sociology, but it's a story. But embedded in that story is all the aspects of serendipity. And I think it is rather sad that in Western science at the moment, stories are stripped out. You submit your paper to a journal, and if you even try and tell the story of how something happened and the steps that led to it, the editors and the referees will throw it out and say, that's not science. Well, I'm sorry, I think it is science, and I think we are missing out. And in fact, we can learn, for example, from the Indigenous community. They understood science, the Australian Indigenous community, but it's embedded in their stories. It's not written in papers for journals. Well, now Ken Kellerman comes into the picture, and Woody to some extent, because it was the 50th in 1983, 50th anniversary of Jansky's discovery of radio waves coming from outside of the Earth. And so Ken organized this brilliant symposium called Serendipitous Discoveries in Radio Astronomy. And at that symposium, in the conclusion, we identified what was in common between the different discoveries being made, and we've written down 6 things. My discovery of Merton was reading one of his papers, and he took exactly the same things and called it the serendipity pattern. He had made no reference to discoveries in radio astronomy. I don't think he was aware of them at the time. And yet it was a perfect match. The same incredible surprise that Claire just described. But for me, it was discovering the serendipity pattern. Now, if somebody makes a prediction of a pattern like this without being biased by any of the radio observations, and it's a perfect fit, to me, that says this model really works. This is not explaining, this is predicting. So I became a Mertonian at this point. So then I saw there was an opportunity here. So in this Mertonian view, and Pawsey was doing exactly the same thing, this explains many of the discoveries. It fits beautifully. I'm not going to talk about any of the details. So I thought to myself, and by the time we got to the end of this book, maybe there's a pattern of missed discoveries. And if we could understand those, that would help us build better research groups because we would know what mattered and what didn't. Now, because of primarily Miller's incredible attention to detail, we know just about everything that happened in Australian radio astronomy in the 1950s period. Every one of those letters and memos and documents Miller has kept track of. So that meant that we could compile a list of missed discoveries. This is not so easy because the missed discoveries are the ones that are not published. There's no fuss made about them usually. And so it's pretty hard to get a complete list. So from the first half of the 50s, here are 5 items which we identified. First of all, Bolton and Bruce Lee had determined that the variability seen in radio stars, as they were called at the time, was caused by ionospheric scintillation. They did that by taking observations at different locations and showing they were uncorrelated. Quite straightforward. And the idea was that they were going to publish that jointly with the Cambridge group. But unbeknown to the Australians, the Cavendish group got together with a group in Jodrell Bank, intending to prove that they were correlated and hence intrinsic, as you might expect if the stars were things like the sun, and in fact showed they were ionospheric. The collaboration agreement was ignored, and this issue here actually caused the biggest rift between the Cavendish and Sydney. The controversy over surveys came later. Okay, a year later, Shane was building a very low frequency interferometer, saw dectometric bursts from Jupiter, said, oh, it's bloody RFI, dismissed it. Another year later is when Mills has got the beamforming Mills cross-working and completely missed the opportunity to use electronic computers to do Fourier transforms. That was the point at which the Cavendish just moved way ahead of Australia in the application of aperture synthesis. So I would say Australia understood, and Pawsey and company invented the concept of aperture synthesis, but they failed to implement it in practice. Then another surprise I got looking at the data is going back to Bolton's first survey paper in 1953. Bolton says, look, the source counts are steeper than what you would get in a Euclidean universe. This might be because there are more objects further away than nearby. However, it's almost certainly caused by the luminosity function. And in one short paragraph, he dismisses it. It turns out, of course, this would have been the discovery of evolution, which Ryle was to make independently about 5 years later. So completely missed by Bolton. Then there was the great discussion of what was generating this radio emission. And in particular, Mills had really understood mechanisms like synchrotron radiation very well, but it's polarized. And the Australians knew that at low frequencies, the radiation wasn't polarized. So, and this is all confirmed actually talking to Jim Roberts, they dismissed synchrotron as a possible mechanism. The Soviets didn't know that polarization hadn't been measured, so it was a perfectly sensible line of pursuit. And so the discovery that radio was caused by the synchrotron process coming from the interstellar medium was missed in Australia. All right, so then I thought, okay, we take all those missed discoveries, what's the pattern? But my disappointing conclusion is there ain't any pattern here. They were all missed for completely different reasons. And I have listed them there. I'm probably running out of time, but since I'm online, I can't see Miller. I can't see Woody waving at me. So I forgot to start my timer. And I think I have mentioned all these points. So that's where I will end, but I will say what I learned from writing the book was not just the history of radio astronomy in Australia, but I became involved in lots of things which I wouldn't known about if it wasn't for writing this book. So thank you, Miller. Thank you, Claire, for teaching me so much. And thank you all for listening to what I have to contribute on this topic. Thank you.
So the next talk is by Ken Kellerman, who many of you know, long time at NREO, back to the 60s. And also very interested in history of radio astronomy, has written a couple of books to do with the history of NREO in particular, and wrote the proceedings of that meeting on serendipity that was for the 50th anniversary of Jansky's discovery of radio waves. And I was at that meeting, but I was only there for the first, tell me when you're ready. You're ready now? I was at that meeting, which I helped organize a bit. Was very interested in it because all these people, these pioneers were there. But I had to leave right after I gave my talk, which was fortunately scheduled for the first morning, because my wife was in labor in Seattle 3 weeks before. The baby was due, and I convinced her that 3 weeks statistically was only a 20% chance. The net result is that our daughter is named Sarah Jansky Sullivan. Okay, so now Ken Kellerman is going to talk to us on Joe Pawsey and NREO. It's recorded, so presumably.
I only met Joe Pawsey once, and I don't think I made a very good impression. It was in 1961 at the IU General Assembly in Berkeley. I was still a graduate student at Caltech. I had just completed an extensive series of observations of radio sources from the Billsley Hill catalog. My observations indicated that the so-called extended radio sources were actually blends of individual much weaker sources. And when I met Pawsey, I think I somewhat arrogantly told him that the Sydney surveys were all wrong. I got a rather cold stare, and that's all I remember about my early encounter with Joe. But of course, I was unaware at the time that Pawsey was on his way to Princeton and Green Bank to meet with Robbie and others and to discuss his appointment as NREO director. At this time, mid-1961, NREO was in real trouble. I think the amount of money that was going to NREO was probably more than was being spent on radio astronomy and all the rest of the U.S., maybe the entire world. There were really no competitive instruments at NREO. Particularly the radio astronomy program at Caltech was far more productive. I remember when John Bolton and Gordon Stanley would come back from Green Bank with stories about the expensive NREO 1,000-degree paraamp receivers. And we'd have a good laugh knowing that the Caltech receivers were only about 250 degrees, far better than the Green Bank ones. Meanwhile, the 140-foot project was being managed, or I guess rather mismanaged out of New York City by AUI, and was years behind schedule and way over budget. Mid-1961 was particularly bad, as it had just been discovered that the metal that was used in the structure was subject to a brittle fracture, and the entire thing had to be discarded. The contractor was fired. Everyone knew that the Parkes and Algonquin Park telescopes were bigger, better, and cheaper. And so if the 140-foot, even if it were completed, which was questionable at the time, it was an embarrassment to everybody concerned. Lloyd Berkner, who was the AUI president who started NREO, was spending most of his time traveling around the world as head of various national and international committees and organizations like the IGU. And he wasn't paying much attention to the NRAO problems. And when he learned about the brittle fracture problem, he just quit the AUI president. And over the next 4 months, AUI had four different presidents. Otto Stewart was the NRAO director in Green Bank. And he was apparently more concerned and more involved in his own research and writing a monthly article for Scientific American and running the observatory. And he wanted to get out. He publicly claimed that NRAO is, and I quote, NRAO is a national observatory in name only, and that there were more powerful facilities available elsewhere. And he said if I were a young astronomer, I would be equally attracted by research opportunities at Stanford, Caltech, and Cornell, and Illinois, and several others. And by the end of 1960, he had resigned as NRAO director. There were no Americans of stature that were willing to accept the job of NRAO director, and there were a few that were even willing to come to work at NRAO, except for a handful of recent PhDs from Harvard that Bach had convinced to go to Green Bank. These were the darkest days of NRAO. In addition to the other problems, NRAO was being sued for breach of contract over the TEL antenna. The NSF contract was up for renewal, and there were serious concerns that the observatory would be closed. And Joe Pawsey was to be the hired gun that would come in and save NRAO. As he mentioned in the book on page 694, Miller asked Frank Drake if NRAO would have turned out differently if Pawsey actually been able to take the job. I think it's interesting to speculate now how NRAO might have developed if Pawsey actually become NRAO director. As described in the book, Joe's ideas about building a synthesis imaging telescope were apparently close to what the NRAO staff was thinking about, especially Dave Heschen. And just prior to Pawsey's visit, Heschen had written a letter to the NSF requesting $3 million to start work on a large array. And as discussed on page 684, both of the Pawsey book and in our book, Open Skies, I think it's curious why Joe, when he wrote to Robbie about his discussions with Drake about millimeter astronomy, but never acknowledged his discussions with the Green Bank staff about a synthesis imaging array. And I think it's also curious why Heschen, who was only acting director at the time, would make such a big commitment to the future and so hastily. It seems that on March 5th, just a few weeks before Pawsey's visit, and without any warning, Heschen called for a staff meeting that same afternoon to discuss the draft request to the NSF to start design work on a large array. And only a few days later, he actually submitted his request to the NSF for $3 million. This was real money in 1961. Perhaps he was trying to cement the idea of a big array before Joe could take a more conservative approach. I think Joe's thinking was clearly less ambition than Heschen's. Can't wait with President, I think, at that March 5th meeting, and perhaps he can comment during the discussion period later. We should also remember that Joe was only committed to NRAO for 3 years, after which he planned to return to Australia. The full extent of the VLA proposal didn't really develop until 1965, at which time Joe probably would have left anyway. So perhaps things would not have turned out differently even if Pawsey had become director. We can also wonder if Joe was as committed to providing a user facility for visiting observers as was Heschen, or was he more interested in a radio physics type atmosphere where staff and visitors could develop their own programs? The more uncertain is how Joe would have dealt with the 140-foot situation. He had already told Robbie he thought NRAO was too heavily invested in big paraboloids. All NRAO had was big paraboloids. The Taylor telescope, which was big by radio physics standards, 85 feet. The 300 foot and pieces of the 140 foot that are still lying on the ground. And remember, the Zond tray NRAO was to construct a very large paraboloid. of the order of 600 feet in diameter. The 140-foot 340 antennas were only meant to be interim solutions. And in 1961, the letters VLA referred to very large antenna, not very large array. And so what would Joe have done as aerial director? Would he have moved away from large dishes? Would he have left the construction of the 140-foot in the hands of AUI and contractor? And if so, what would have happened? And remember, at that time, AUI was somewhat dysfunctional. Or would he have taken over the responsibility himself as adhesion? And if so, would he have abandoned the equatorial mount? I think what we all agree is a sensible change to an outdated construction, probably using the park site for master equatorial for coordinate conversion. Or being against large graveloid, would he have just canceled the project? We could also wonder if Pawsey would have moved the observatory headquarters to Charlottesville, or would he have succumbed to Robbie's pressure to move to a more intellectual community like Princeton, or would he have just kept RAO in Green Bay? In any event, I suspect that as planned, Joe would have left after his 3-year agreement and returned to Australia, perhaps with a cushy job in Canberra or in industry, or maybe even ultimately to succeed Bowen as radio physics chief. He too probably would have become director in 1964 instead of 1962, and NRAO today would probably not much different from as it turned out. So thank you.
Thank you, Ken. Our next talk is by Rebecca Oppenheimer, From Optical to Radio and Back to Optical, Interferometry.
Thank you, Woody. You might be wondering what the hell is some crazy person from New York City who mainly works in the optical and IR is doing up here. But it's a real honor that I was asked to do this because I got my start here at the VLA. This is the first observatory I ever worked at. And I did radio astronomy, in fact, into part of graduate school, in fact, with the VLA. So I just wanted to give a slightly broader view from someone, I guess, sort of outside of radio astronomy. I mean, I love it, but I particularly love interferometry. And I think all of astronomy, not just radio, owes a debt of gratitude to those early interferometric experiments. So just to go back a little bit in history, interferometry was discovered with Young's double slit experiment in the 1820s. Of course, they didn't call it interferometry, but this is what spurred the wave-particle duality of light and led to all kinds of really interesting science. But it wasn't really until the 1920s that people even considered using it in astronomy to look at things off of the planet. And that was done in the optical, actually, by Michelson and Pease. So Michelson was famous for the experiments showing that the speed of light is constant in all directions and there's no ether, very fundamental result. But he also spent a tremendous amount of time doing optical interferometry of stars using the new 100-inch telescope on Mount Wilson. He stuck this huge beam, it's a 20-foot long beam, with 2 little mirrors on it and 2 relay mirrors. So in this case, you're taking 2 tiny mirrors and you can change the distance between them. So you're changing your baseline, pointed at a star. So you're not using the primary mirror except to combine the 2 beams and interfere them at a little eyepiece off to the side. And that, I don't think this may be Pease, I'm not sure who it is, but this is an example of how you did interferometry in the 1920s. Now, so the cool thing is you don't need a delay line or any of this complicated stuff because the path lengths are exactly the same. And as you observe, you can change your baseline. So what they would do is look at a star, change the baseline until they saw the fringes go away or reappear. And that's how you would determine the diameter of a star. In fact, they did this for about 10, 15 stars, and there's a very funny description. Well, I mean, I don't think he would find it funny, but this was ridiculously difficult to do. I mean, you'd spend many, many nights on single stars just trying to figure out what was right. You needed really good seeing. Mount Wilson, surprisingly, has excellent seeing, so it was a good place to do this. So, and oh, there was another person who would hang on, I don't know, there was some structure, I can't remember exactly where it is. If you go to Mount Wilson, you can actually see where that is. That person would turn a crank, so the observer would yell, okay, change the baseline, and they had another little magnifying thing that they could look through, and there's a wooden ruler with inches marked, you know, just like a school ruler, and the observer would mark down, okay, it's at 18.2 feet, and they would mark that down. This was data collection. So this was just way too hard, and they gave up in 1921. So after that, pretty much nothing happened in astronomical interferometry until the radio. And the key with the radio, and I think what a lot of the people, especially in Cambridge and Australia, realized, and I think Pawsey realized this, is that you don't have to worry about a lot of the crap that you get in the optical. And that was the key, because you could do this with actual detectors, radios, right? Instead of your eye and writing little notes down. Oh, the fringes went away at 18.2 feet. But keep in mind also, a few people have kind of mentioned this, no one ever believed this stuff would work. The experiment by Michelson and Pease worked, but it was so limited. Basically, people thought, well, they did everything you can do with interferometry. Obviously, this is completely false. What the Cliff interferometers did was show that you could do this with astronomical objects following the sun. And I think I would say it's due to these intrepid instrument builders who said, to hell with all you people, we're going to try this, and they did, and it worked. But you know, the VLA, of course, also was predicted never to work. It was impossible, it's crazy, never would work. So I believe that these things really, they're the path that we've come to now. And it's my impression and my belief, because interferometry is by far the most sensitive measurement we can make of any celestial object. It will dominate. In fact, I believe there will be very few single telescope observatories 100 years from now. Everything will be done in interferometry. Maybe, you know, there's obviously some real technology that needs to be built. Doing this in the X-ray is extremely difficult, even in the UV. But for example, right now, there are tons of interferometers in operation, all the way down into the optical. So this is the Char array right next to where Michelson and Pease did their experiments in the 1920s. Incidentally, there were several other attempts to build optical interferometers here in the 1990s as technology started developing some control mirrors and better sensors and all of that. This has 6 beams. The call for proposals from the general public just came out. Proposals are due very soon. It's 45 nights, open to anyone. Obviously, ALMA. That's the NPOI, the Navy optical interferometer. There's, of course, another one just a few mountains over in Magdalena. That's the VLTI, so that's 4 8-meter telescopes doing routine optical and infrared interferometry. And there are many, many more being planned to be built at this time. As you know, some of the proposals for NGVLA and all these other things, square kilometer, you name it. And I'll just highlight the power of this. So going back from looking through an eyepiece to measure stellar diameters, these are a few results from Chara that I just picked because I like them. These are actual images of these stars. They're oblate. These things are spinning like hell. They have different temperatures at the poles than they do at the equator. Vega, our standard star, probably is comprised of 7 or 8 spectral types. It's not just A0. People are now imaging spots on some nearby stars. Then you see weird things. This thing has been known to have a weird eclipsing event every 20 some odd years. They imaged it some years ago, and it looks like an imperial cruiser is passing through. It's actually not known what that is, but it's probably another star. This is a relatively young star that is embedded in a disk that is also orbiting that star. So this is weird stuff. On the far right, you can see Beta Lyrae. This is an interacting binary where one of the stars is beginning to evolve into the giant phase. And you can actually see the large one is filling its Roche lobe. For those of you who don't know what that is, as a star expands, if it's orbiting another star, there's a gravitational kind of shape that it can fill before it starts spewing its material onto its companion star. This has been theorized for many, many years. We can actually see it now. I mean, this is really far out stuff, and I'd like to believe that Pawsey would be very excited about all that. And I'll just finish up with one personal note. So I actually got the Michelson interferometer to the museum in New York where I work. Had an exhibit on various techniques to, I'll be done in a minute, to study planets around other stars. That's the beam suspended up there. We've now shifted back to Mount Wilson, but there were approximately 4 or 5 million people saw it. And we had a lot of information on how interferometry works. So don't believe anyone who tells you that it's impossible to talk to the public about interferometry. It's absolutely false. Yeah, just to reinforce what I said, really what you want to do in astronomy is measure the full electric field from whatever object you're seeing. Not just record photons, not just do polarimetry, but do everything, right? So that is what I think interferometry gives us. I mean, the VLA does that. And just for fun, we now do have an interferometer in space. This is a non-redundant mask for the Webb telescope that we prototyped in my lab in New York. And a final version of it was put on JWST, and it works. We can do these really nice interferograms of stars. So you see here, this is the mirror pattern from JWST. You're blocking most of it out and picking a few the open segments to do your interference. So thank you very much. That's all I've got to say.
Thank you. I'll just remind you that after the next talk, which is the last one, we'll have time for questions for any of the speakers or general comments about the whole afternoon before we have a small reception. And in fact, Harry Bent, who has authored several books together with Miller and others on the history of radio astronomy, his title is Pawsey, Summing Up.
I apologise in advance. I'm going to read, otherwise I'll never do it in 10 minutes. So a hard act to follow, and lots of information. I'll sort of share my impressions of the book and things that were my takeaways. That's how I would really sum up what we've heard today. So you've heard Hastings talk earlier about Pawsey's background and his mother's influence, particularly on his education. It's hard to believe that before 1948 you couldn't do a PhD in Australia. and you needed to go overseas. And luckily for Joe Pawsey, there was a series of scholarships that he was able to avail himself of that made that possible, and it made it possible for him to go all the way to Cambridge, which was really the beginning of his international connections. So he had that, great background coming from Australia, but arriving in Cambridge was really, really a key event. There were only 7.3 million people in Australia in 1945. And as an island continent, it was particularly isolated. And that isolation meant that communications technology was incredibly important. The Australian Radio Research Board was founded in 1927, and it built a reputation and attracted a lot of key researchers, one of which was David Martin, who you've heard mentioned earlier. And they built a practice of ionospheric research, and that also was the topic that you heard earlier of Pawsey's PhD thesis. And that work of being an isolated nation and needing to rely on radio communications was the basis of why the ionosphere was studied, because it was the means in which radio communications occurred. And so despite Australia's isolation, it was actually well placed as events moved along, where you had a core expertise in ionospheric research, and because of pursuing that, also expertise in earlier radio development. Pawsey's first job was, after he completed his PhD, you would have heard as well, was working on the aerial feed lines for TV in Britain. And with that relevant experience and his desire to return home with the onset of the war, he was quickly recruited into working in radar in Australia. And that was part of the Council of Scientific and Industrial Research, the CSI, which was the forerunner to the CSIRO, and the Radio Physics Laboratory. Pawsey's work developing the unique lightweight air warning radar gave him hands-on experience working at not only at pace in wartime, but dealing with the politics of how do you work with the Army and the Air Force, which is not an easy challenge. He also travelled to the US during that period of wartime to learn about centimetre wavelength technology that the British had shared with the US, with the cavity magnetron being developed. And it was really this wartime working pace, in Australia, the Japanese bombed Darwin, which was a real wake-up call. At that point, there was no early air warning radar. They concentrated on basically detecting shipping, not aircraft. And radio physics quickly had to pivot to help support that. And it's in that environment, Pawsey was working and developing the technology that would later birth radio astronomy. There's two people I've mentioned that probably only got touched on earlier, one of which maybe not at all, that were really critical to that transition of the end of war to what would happen in peacetime. First of those was David Riddett, who was the CEO of the CSIR. He had the challenge of saying, what are we going to do post-war? Where will we focus research? And he firmly believed in backing basic research and that it should be separated from military research. It was reasonably controversial at the time. And he also was a strong proponent of freedom of expression in scientific matters. And you can see that sort of that Newtonian scientists in Rivet as well, in a lot of his beliefs. But that came at a fairly high personal cost, because that was sort of a period when Australia's version of McCarthyism was starting to take hold as well. And he came into a lot of criticism for his ideas of sharing scientific discovery and research internationally. But fortunately, he persisted, and CSIRO then focused from that point on to peacetime research. At that very time, Taffy Bowen, who you've heard of, became the head of radio physics at that transition point. Bowen had been involved in airborne radar in Britain during the war, and he was part of the Tizard mission that shared the secret of the cavity magnetron used for centimetre radar. And he became head of the radio physics laboratory right at that time. Bowen's, and Bowen's entrepreneurial skills and his reputation in radar development, and you couple that with Pawsey's scientific leadership would become a really powerful combination going forward, and would lay a foundation for Australian radio astronomy. We talked about serendipity. I really like Lewis Pastor's quote that in fields of observation, chance only favours the prepared mind. So it's not just about being lucky. You actually have to have a preparedness to understand what's coming. And under Bowen's guidance, radio physics proposed exploring a wide range of peacetime activities. So they looked at everything. They sort of cast a wide. So looked at rain making, they looked at navigation aids for aircraft, all sorts of things. Computers were pursued. And one of the areas that they looked at was that there'd been reports during wartime of interference from radars from like the sun, and of course they knew of Jansky's discovery of emission from the galaxy. So with that, and particularly in Australia at that time, there've been reports from New Zealand from Dr. Elizabeth Alexander. Weren't many women, but it's interesting that Elizabeth Alexander and Ruby Payne Scott were two very prominent women in that time in an emerging field, and particularly in that when it was such a male-dominated area. And they came right at the time when wartime had finished. The Australians had been developing radars at a range of stations and were working closely with the military. And one of those stations was at Collaroy Plateau, and you saw earlier from Hastings' talk. And on the 3rd of October, as you heard, 1945, they basically used their own receiver. They built, Lindsay McCready built a slightly better sensitivity receiver, and they used it on a 200 megahertz coal radar to detect the sun. Most of the observations, actually, they were smart. They used the Air Force personnel to do the observations in the early morning and the late afternoon, and they did the data correlation. The interesting thing in all this is that those observations actually began right at the start of sunspot cycle 18, if you're familiar with sunspot cycles, or since we've been counting them. And quite fortunately, there was a local maximum within days of that. So they were fairly quickly able to determine that there was a correlation between sunspot numbers and the variable 200 megahertz emission they'd observed. And they noticed that that variable emission didn't fall below a baseline. And, if it was thermal in nature, that temperature indicated it was much, much higher than the photosphere of the sun. David Martin, who was working at Mount Stromlo at that point in time, had proposed a theory for the million-degree corona temperature, and they fairly quickly were able to publish the results, and that was the first paper that appeared in Nature. So I might move there. Just wanted to talk a little bit about Pawsey's influence. The book up there you've seen held up earlier. In the first 5 years of radio astronomy in Australia, there were 51 papers published, and they appeared in 10 different scientific journals. Pawsey was first author in only 5 of those, and he was the second author in 1, so making 6 in total. He was, however, specifically acknowledged in over 16 other papers where it was saying they specifically acknowledged his contribution in both the experimental design and the discussions in that. So if you look at that, in that first 5 years, 43% of that published research, Pawsey had a direct hand. So not only was he administrating, he was very, very actively involved. It's my measure of his influence. The interesting thing, it wasn't only within radio physics that he had that influence. That was across papers that were published by Stromlo, University of Tasmania, and the University of Western Australia. And that really demonstrates to me Pawsey's openness and willingness to participate. It wasn't just about his group. It was much, much broader than that. And he had the ability to manage some really tricky priority situations with Martin, for example, who did Pawsey's observation first indicate the million-degree corona, or was Martin's theory? Pawsey was above the argument of who's to take the credit for it. He just, went with the science and demonstrated that. And his influence wasn't just in Australia. It was, he actively sought out and built international connections and made sure his team did the same. Another point, example for me was his strong scientific integrity. And a good example of that was in Mills in 1952 was publishing the design of his Mills Cross. He made sure that Mills acknowledged Ryle's invention of the phase switch. And at that stage in Australia, Ryle hadn't published any details of the phase switch. They'd only heard the rumours. And as it turned out, Mills's implementation of it was physically different, conceptually the same. But Pawsey insisted that Mills acknowledge Ryle's contribution, even though it was only a rumour at that stage in the paper. That says to me he was always particular on acknowledging the contribution of other groups. And I think, his willingness to share, although it was only published in 1955, it took a while to gestate. The book on radio astronomy was the Bible at the time, and it demonstrates the willingness of that group to share. Let's talk very briefly on his legacy. I think Pawsey demonstrated the success of what we call today the learning organisation. It's small independent groups, shared learning, bringing it together, was actually ideal for that discovery phase of radio astronomy in the very early days. Try lots of different things, follow the successful ones. His open internationalism, should mention, acknowledge that, he really helped kickstart Indian radio astronomy. You saw David Swimmer was, trained at Pawsey, actually donated that instrument. You saw the grading array to India in later years to kickstart the development. And although Bowen and Pawsey, had read about it in the book, the fallout in the later years with the development of the Parkes radio telescope, ultimately that fallout led to the seeding of a lot of other, astronomers from radiophysics into the universities in Australia and really spread that group. So I actually think from, something that was fairly negative, that's a very positive outcome of involving Australian universities much more in radio astronomy. Pawsey's honoured today through the Pawsey Medal, which the Australian Academy of Science awards for early stage research in Australia. Miller's a recipient of that medal, I'd like to acknowledge. The Pawsey supercomputer in Western Australia, which is supporting the square kilometre array development, is obviously named after Pawsey. If you're an amateur radio developer, you would have heard of the Pawsey stub, which is a little device for connecting unbalanced feeds to balanced serials. However, I think Pawsey's biggest contribution is really the people and the ongoing development of radio astronomy, and the people he trained went on to develop and grow in the group. So finally, I'd like to, my picture of this is a very historical photograph because it was during COVID. We snuck out to take this photograph at sunrise, which you can see the sun rising over the ocean. To recreate 75 years after the first event. And you can see we had to sneak through the barriers because it was still a construction site. But here's Hastings standing next to the, Hastings put in an amazing effort to convince the council to build that, and Woody will be pleased to see the analemma in the to give the nod to the solar observations in the construction. And I'd like to leave it at that.
Marvelous summing up. Who wants to go first with either a comment or a question to any of the speakers in this great afternoon? Is it really?
And we have a comment from the Zoomers.
Absolutely.
This
Please.
is Jim Moran. I actually have a question for Cam Wade, who I believe is in the audience. Is that correct?
Yes.
Unfortunately, it is.
I want to hear Cam's comments on the events of 1962 and the development of interferometry. In the summer of '62, I was a undergraduate summer student at NRAO, and Cam was one of the prominent lecturers. So he became a mentor and somebody I admired very much. There was hardly any information given on all the exciting things that Ken told us were going on in thinking about interferometry in that spring of 1962. We knew about the 140 foot because the axle was lying on the ground. But could you tell us what was happening in the thinking of the NRAO staff in the spring of 1962?
Well, it's been a long time. I don't know how many people in the room were around at that time, but I was a very junior staff member at that time. I had done my postdoc in Australia, and Joe Pawsey was my boss. And I developed a terrific respect for him. He impressed me, I've got to say, as a total gentleman in every way. He was not driven by ego like some other people in the business were, but he was always a person who seemed to know what was going on. And so now it's back to the 1962 bit. What? I have no specific memories, but I do know they had to basically scrap the 140 foot telescope at its present state of construction. And there are some very expensive culverts around the Green Bank Observatory right now. And that was, I guess, as good a fate as they deserved. I think it hit the limits of my memory.
Thank you very much.
Cam, I can see the back of your head. Why don't you stand up and take a bow?
Cam, I'm more interested, as I indicated in your comments, your recollection of the events of March the 5th, 1961. You were present at that meeting. Did you know about this memo before you received it, presumably on the morning of March the 5th?
Let's see, are you referring to the coffee break where we decided we should do something like the BLA? That was in '61. I'm not sure exactly what you mean.
Well, the Dave Heaton circulated a memo. It was dated March the 5th, 1961. And he said, I'm calling a meeting for this afternoon to discuss this memo. And there was, I don't remember, a 2 or 3 page memo, a letter rather, to the NSF requesting $3 million. And he mailed it a few days later. So you're the only one left who I believe was present on that day.
Well, I can say anything I want without fear of contradiction. I have such a very sketchy memory of that occasion. A lot was going on at that time. And honestly, I don't think I can say anything useful about it.
Other questions or comments?
So,
well, if not, let's give a round of applause for this fascinating afternoon and talk.